Okay, everyone. In this screencast, I'm going to review the answers to the limiting reactant worksheet, as well as give you some pointers when solving the limiting reactant problems. On number 1, I would say this is a pretty straightforward type of problem where the amounts of reactants are given to you in moles. The most important thing with any stoichiometry problem is to make sure that you start with a correctly balanced equation. So double check to make sure that you are remembering that chlorine gas is diatomic and that you have the equation balanced. It will be expected when you take your exam that any question that does involve a limiting reactant, that you set up an ice diagram as your work to show what is limiting and what is excess. So please remember that. This top line here, remember, represents the mole ratio, which is obtained from the balanced equation. Once you fill in the initial amounts, which are given in the problem as 2 moles of sodium and 2 moles of chlorine, you need to think about which one of these is going to run out first. And that's going to be dependent on both the initial amounts given and the mole ratio. So since the mole ratio is 2 to 1, and you have 2 moles of each, it's obvious that you're going to run out of the sodium first since you're requiring twice as much. Another way that you could think about looking at a problem like this to figure out what is limiting is to kind of cover up one of the reactants and ask yourself, well, if I had 2 moles of sodium and it's a 2 to 1 mole ratio, I would only need 1 mole of chlorine, and since I have 2, the chlorine must be excess. So that means by default that the sodium must be limiting. Now remember, the reactant that is limiting always goes to 0 on the end line, and in order to fill in the change line, you're going to subtract all of the initial amount to get that 0 on your end line. And then most importantly, to remember that the mole ratio up here and the change line follow the same stoichiometry. In this particular question, it's literally 2 to 1 to 2. But that just happens to be a coincidence. As long as the mole ratio is followed on the change line, you're going to be fine. For example, 2 to 1 to 2 down here could be 4 to 2 to 4. So just keep that in mind. That's the most important part about filling in your ice diagram. Once you have your change line filled in for the sodium, obviously you can go back and fill it in for the chlorine using that 2 to 1 ratio and then the 1 to 2 ratio for the sodium chloride. Another big thing to remember, the reactants are always going to be a negative on the change line because you're consuming those reactants, and the products are always going to be a positive because they are being produced. For part C, you want to pay attention to the unit. You need to have your answer in grams, so make sure you show a little T-chart as you're converting moles of sodium chloride to grams. Part D, you need a particle representation. Now, the big thing about particle representations is to make sure you always include what you have at the end of the reaction. And in these reactions that involve limiting, you have to remember to include whatever you have in excess. So we look at our end line, we need to make sure we include the chlorine in excess, which would be a gas. It is diatomic, so I'm drawing it this way. And as far as the solid is concerned, just make sure you have like a pile, like a shaded area labeled as solid. You don't have to worry about drawing like a particle representation of sodium chloride or anything like that. Just draw a pile of stuff at the bottom. Number 2, again, pretty similar to number 1, nothing that's really crazy. You do want to make sure you start with your balanced equation. Again, that represents your mole ratio. Your givens are both in moles, so a little bit easier. You do have some extra information about the volume of the tank and the temperature, which is going to come in at the end. As you fill in your ice diagram for this one, you may need to do a little side work to figure out, this number here, 1.33. It's not expected that you can figure out the change line in your head. So off to the side, do a little T-chart out to figure out that number. Keeping in mind that obviously we have to figure out what is limiting first. Based upon the fact that this is a 1 to 3 mole ratio, I would need to have 30 moles of hydrogen if this was going to react perfectly. And since you only have 4, the hydrogen by default is limiting. Once you consume all of this hydrogen here, it drops to 0 at the end. And you're setting up a little T-chart to show that you're starting with 4 moles of hydrogen, but for every 4 moles of hydrogen for every 3 moles of hydrogen that react, only 1 mole of nitrogen is needed. So it's 4 times 1 for the nitrogen divided by 3 is where we're getting this 1.33. And then obviously, same as before, we're subtracting that to get our end amount. And then we're using our stoichiometry here to get our amount of ammonia produced. The easiest thing to do is look for the 1 to something ratio to figure that out. So if it's 1 to 2, and you know the change line here is 1.33, we're doubling that to get the 2.67. And then again, remember, you're going to have a positive sign on the product side because those products are being produced. Part B, they want to know what is in excess in the mass. Remember, grams is for mass. So again, one of the other problems that you might have ran into here is forgetting that nitrogen is a diatomic gas. So that's why we have 28 grams per mole for the nitrogen. And for part C, we want to know about the total pressure. Now, the total pressure in the tank at the end is due to any gas that is present. So when you look at your end line, one of the things we probably should have done is put in your phase symbols here. That's why those phase symbols are going to be really important. These are actually all gases. But what gases do you have at the end? You have nitrogen and the ammonia gas. So the sum of these 2 moles is where we're getting, hold on. Oh, sorry, I'm on part C. Part C is the partial pressure of ammonia. So for partial pressure of ammonia, we're just going to use this number into PV equals nRT, the 2.67 moles. For part D, when we need the total pressure, that's down here. That's where we're using this 11.4 moles. The 11.4 is the sum of the 8.67 and the 2.67. So pay close attention to what you're being asked. Partial pressure, go back to gas laws. It's just the pressure of an individual gas. Use PV equals nRT. Just plug in the moles of that individual gas. If you want total pressure, pay close attention. Anything that's a gas, whether you're talking the product that's a gas or something that's in excess that's a gas, has to be included in the total pressure. And obviously don't include solids and don't include solutions. You're just including gases. All right, so for number 3, this is the first time that we're actually seeing a problem that is not given to you in moles. We're giving you the mass of magnesium and we're giving you the volume and the molarity of the solution. So the first thing that you'll have to do, kind of off to the side, we call this our side work, is convert the mass of magnesium to moles. Now, when you look this up on the periodic table, the molar mass is 24.3 grams per mole. So if you have 2.43, you obviously have 1/10 of a mole. For the moles of hydrochloric acid, you would need to use your molarity formula. Molarity is moles over liters, so make sure you convert this to liters. It's going to be 0.1 liters. So 0.1 times 3 is where we're getting this 0.3. Once that's figured out, you can figure out what is limiting. Again, a 1 to 2 mole ratio here says that I would only need to have 0.2 moles of HCl for all of this magnesium to react, which I have plenty. So my magnesium will be limiting. Remember, your change line follows your stoichiometry of your mole ratio, which in this case is the 1 to 2 to 1 to, the 1 to 2 to 1 to 1. And then the other most important part of this problem is to make sure that you remember that at the end, when you make that 0.1 moles of hydrogen, since the conditions are at STP, you can make your life a little bit easier by remembering that 1 mole of any gas at STP is 22.4 liters. That's why I'm going to use that as my simple conversion factor to get my final volume of 2.24 liters. Now I want to remind everyone that I already did out number 4 in an earlier screencast where I did out the problem from the beginning. So if you're really having any trouble with number 4, you can go back to the Introduction to Limiting Reactant screencast and you can check out this problem there. But we're seeing, something similar to number 3 where you have to convert the mass of sodium to moles, and that's done first. Then you have to convert the volume of water essentially to moles, remembering that the density is 1 gram per mole. So 100 milliliters of water is 100 grams of water, and then we convert that to moles. So it's just 2 conversions from grams to moles. Once we know that, our stoichiometry is 2 to 2 to 2 to 1. So we can see that we're going to be running out of our sodium first because the mole ratio is the same between these two, and the sodium is the one that I have a smaller amount of. So I'll use my change line to subtract all of the sodium to get 0 on the end. Use my stoichiometry 2 to 2 to get the minus 0.87 here. When I move over to the product side, remember this is going to be a plus because we're making more. We started with none, we're making some. And again, still just using the stoichiometry here to fill in my change line. While we're talking about filling in these ice diagrams, I do want to remind you that the ice diagram can be filled in any unit that is proportional to moles. So depending on the conditions, if the volume is constant, you could fill in the ice diagram in pressure. If the pressure is constant, you can fill in the ice diagram in volume. Obviously, temperature would have to be constant in both of those scenarios as well. The last thing to remember is, again, when you're getting your answer, which should be mass, remember that hydrogen is diatomic. It's H2. So you're going to be multiplying that 0.44 by 2.02 grams per mole. Please make sure you're also showing all of your steps for your conversions between units, like grams and moles and liters and moles and all of that stuff. All right, here. For number 5, I know some of you may have been a little perplexed as to why there was a fraction as a coefficient, because we told you that you couldn't do that. Well, it turns out that you can do that we're not typically going to have fractions as coefficients, but it can be done. So that's okay. It's supposed to say 3/2. Now, when you look through the problem, you have your 75 grams of iron, which the first thing that was done was it was converted to moles here. Again, show your work for the conversion from grams to moles. And then the second thing that has to be done is, because you're given the volume of oxygen and it's not at STP, you will have to use PV equals nRT, which is what this is over here. PV equals nRT, plugging in the value of pressure, temperature, and volume to get your moles of that oxygen. So that's where this 1.25 comes from. Remember, your initial amount of the iron oxide is 0. All right, so we've got number A. For B, we need to figure out what is limiting. Again, same as before, we've got our mole ratio. We've got to figure out what these numbers are. Don't be afraid to do out your work off to the side. You're not expected to be able to do this in your head. Once we figure out what is limiting, which in this case happens to be the iron, the question is to calculate the number of moles of iron oxide produced. So essentially you just have to keep filling in that ice diagram and getting all your boxes filled in, and you're going to get your answer of 0.67 moles. For the last part, as you draw your particle representation, we do want to remember our particle representation represents everything at the end. And at the end, we have no more iron, but we have some oxygen, so you'd want to draw that in. And we have a solid iron oxide. So again, phase symbols would be required on all of these. Iron is a solid, oxygen's a gas, and this is the ionic compound iron oxide. And that would be a solid because it's an ionic compound and there's no water present. All right, number 6. This one's a little bit different from all the ones that we've looked at before because I'm not giving you both amounts of reactant and asking you to figure out what is limiting. I'm asking you to figure out what is in excess using one amount of reactant. We know that we have 3.9 moles of HCl, and we don't know the amount of sodium phosphate, but we know how much product is formed. We know that we made 1.0 moles of phosphoric acid. So this 1.0 moles of phosphoric acid, which we technically should be writing in here, tells me what the change line is. My change line is 1.10 moles. Because remember, I had 0 here and I had 0 right here to start. So if I know my change line, I can fill in anything else on the change line using stoichiometry. So if it's a 1 to 3 ratio, I can figure out that I must have consumed 0.30 moles of hydrochloric acid. And if I know I started with 0.9 moles, I know that this must be in excess. Now, if I had consumed all 3.9 moles, then the HCl would have been limiting, and then by default, the sodium phosphate would have been in excess. Another interesting thing about this question that's not filled in is you could figure out exactly how much sodium phosphate you would have needed to react and how much actually did react, because we know the change line. If this is 3.30, this is 1.10, and if it all gets used up, this initial amount of sodium phosphate would have been 1.10. So there's a lot of information that you can obtain from an ice diagram. It's not always going to be a typical, here's the both amounts of reactant, just figure out what's limiting. You may be given situations like this where you have to work backwards, and you'll be given different parts of the diagram as clues to fill in the rest of the diagram. I like this one. All right, number 7, another good one, has a little star next to it. The College Board gave us this example. This one is for you to remember that pressure is proportional to moles. And that if pressure is proportional to moles, the pressure ratio can tell us the mole ratio. So in this case, when these two gases are mixed, it's a fixed volume. So there we go. We know it's a fixed volume. The temperature is constant. So that gives us the go-ahead to say pressure is proportional to moles. The initial partial pressure of the fluorine was 8 atmospheres, and the xenon initial pressure was 1.7 atmospheres. What we do know, and this is our big clue, we know that the pressure of the unreacted fluorine was 4.6 atmospheres. So everything in black is given. So once we have all of this information in black that's given, we can clearly see that we can fill in this change line. Once we know this change line here, we obviously know the fluorine is also in excess. So we know our pressure here. Now the pressure here, we know this also has to drop to 0 because remember, if the fluorine is excess, the xenon is limiting. So we know this has to be 1.70. We know this is 3.4. It's a 1-to-2 ratio on our change line, which means our mole ratio is also 1-to-2. Now, knowing our mole ratio is 1-to-2, we had 1 xenon and 2 fluorine. So that means we had 1 xenon atom and 4 fluorine atoms on the reactant side. So that means our product must be XeF4. Remember, conservation of matter. We can't just create matter or destroy matter. So this is a good question to allow you to practice using pressure ratios to get mole ratios and then to solve for an unknown formula. Kind of like what we do when we do that combustion analysis. We use mole ratios to work backwards to conserve matter to get the formula of our unknown compound.